Hello, everyone. Welcome to tonight's session on SN1 and SN2 reactions. Before we begin, if you were here last week and you remember the nightmare of a time we had with technology, I think I got most of it set up, but if we do run into any issues, if the audio cuts out, if I get disconnected, I appreciate your patience. I was so impressed that everyone stuck around last week. And so I will do my best to get reconnected as quickly as possible. And let's learn about substitution and, well, not elimination. That's not this week. That'll be next week. So let's talk SN1, SN2 reactions. I already saw in the comments that some students are having exams tomorrow, next month. Sometimes when I do a session and you're here, but it's a topic you're covering later, I recommend logging off because you'll get overwhelmed. This topic, though, if you are approaching substitution, if you're already on alkene reactions, for example, then this is the kind of session that you will not be overwhelmed sticking around, and this may actually be helpful. And so it's up to you if you want to stick around. For example, Angel, knowing where you are, I do think this will be helpful. And so if this is coming up soon, today is a beginner session, and you are going to learn so much. Jessica has an exam next week, so this is perfect timing. I also saw somebody's testing tomorrow and a couple more very soon. So let's go ahead and jump right in. Welcome to today's session on SN1 and SN2 reactions. This is the first half of what is the most complicated, difficult topic in Organic Chemistry 1. The first half because elimination is the second half, and that will be part 2. So looking at substitution, one of the reasons this is more difficult is if I take the reaction right here, you'll notice that I have the same starting molecule, an alkane with a chlorine on it. If I react it with H2SO4 in water, the product is going to be an alcohol. If I react it with NaOH in DMSO, the product is going to be the very same alcohol. The difference here is that the first one is an SN1 reaction and the second one is an SN2 reaction. Now, in this case, it doesn't actually matter because the starting and ending molecules are the same. But as it gets more advanced, the reaction will go in a different direction depending on what is going on. And the way most students approach this is memorizing a flowchart that doesn't always work. And that's where things get confusing, especially when we bring elimination into the mix. If you are just joining, welcome. We're covering SN1, SN2 reactions. Don't worry about copying down everything that you see on the screen. I've got you covered. Just put live notes in the comments and I will respond with a link. That's not what I meant to do. I will respond with a link where you can sign up to get a copy, a PDF of everything that you see me drawing tonight. Yes, even if you're watching the recording. So let's go ahead and break down the individual reactions so that you understand what is going on, why it's happening the way it is. And if you can understand it, then the rest of it is going to be not necessarily easy because it is a hard topic, but it will be a lot more doable. So we'll start with the SN1 reaction. Let's break it down. The S stands for substitution, where we swap one thing for another. The N stands for nucleophilic, and the 1 tells us the rate of the reaction. This is a unimolecular reaction. Unimolecular, not uni-step. Be very careful. This is one at a time, which is really, really important. Substitution means that we are going to swap something, and a nucleophile is the type of molecule that we're using. If you haven't reviewed this yet, make sure you understand what is a nucleophile, because this comes up in quite a few topics. Don't just memorize it, understand it. Nucleo comes from the word nucleus. The nucleus is the center of the atom, where in the nucleus you will find a mix of protons and neutrons. Protons are positive, neutrons are neutral. For the sake of this discussion, we care about the positive. A nucleus is positive, and phile meaning loving. This is really, really important. A nucleophile is a molecule that is nucleus loving or positive loving. What kind of molecule loves and is therefore attracted to something positive? If opposites attract, then what we're looking at for the nucleophile is something that is negative or partially negative. The delta means partially. So we're looking at a molecule that is negative or partially negative. It will then be attracted to the positive, whatever it is that we're reacting. And this is the key behind this reaction. Now, the nucleophilic substitution is SN1 and SN2. Let's continue talking about SN1 first to make sure that we are on the same page with this reaction. Let's go through the mechanism step by step. We'll go through the SN1 mechanism, starting with the molecule that I had given you before, but I'm going to change it up a little, and I'm adding a branch here. The reason I'm adding a branch is this is important. I want to be able to talk about a few more things that come up. If I react this in a solution of H2SO4 with a solvent of H2O, typically you're given your reactant, the thing that attacks, the thing that will initiate the mechanism, at the top of the arrow, and you're given your solvent at the bottom of the arrow. This is the solution, the liquid where all of this is taking place. So what is the nucleophile? What is the attacker in this reaction? This is a trick question. Hi, Sydney. I'll take that as a good thing, right? This is a trick question because even though H2SO4 is written here, you should recognize that H2SO4 is sulfuric acid. An acid is positive, not negative, not a nucleophile, not going to attack anything. Anytime you see an H2SO4 in some kind of solution, that is simply an acid catalyst that is going to help with the reaction, but it will never attack anything. An acid catalyst is simply a source of protons of H plus in solution. And if we can protonate the solution, protonate what is going on, that will help with the reaction. Which brings me back to the question, what is my nucleophile here? It appears we're not given anything else because H2SO4, as I will repeat over and over, is not the attacker. It is oxygen, absolutely correct. It is oxygen in the solvent. So this is a tricky situation where this is called a solvolysis reaction, salvolysis. Salvo is the solvent, lysis means to break. The solvent is the attacker, the thing that's going to break things and attack things. We have so many water molecules in solution that if I take one of these water molecules and I look at what I have, I'm going to do the mechanism again because I'm drawing too much over here. Let's take a look at this water molecule. We have an oxygen with two hydrogens attached. This right here is a polar bond. It's a polar covalent bond. And that means even though the molecule is neutral, hydrogen is very partially positive and oxygen is very partially negative. That is because oxygen is pulling on all the electrons between itself and hydrogen. It's hogging the electron density, making it reactive. In a solution where I don't have something more negative, I don't have a negative charge, the most negative, the most nucleophilic, the most basic, the most reactive, same definition, is a partially negative oxygen atom. And this one is also partially positive because the electron density is being pulled away from that hydrogen. So this right here is going to act as both the solvent, the solution that everything is in, and as my nucleophile, as my attacker in an acidic solution where I have just positive and neutral, never negative with an acidic solution. So let's redraw the molecule and take a look at the mechanism. In a situation like this, where I don't have a strong attacker, water is just kind of hanging around that may or may not attack. It's kind of minding its own business. What I also have to consider is that chlorine right here is sitting on the molecule, but it is highly electronegative, very, very highly electronegative. It is greedy. And it starts to pull on the electron density. It starts to pull on the bond between itself and carbon. And it's pulling and it's pulling and it's pulling until eventually it pulls so hard, it just breaks away. It pops off. And what I'm left with here is a carbon chain that now has a positive charge at the tertiary position, and then a Cl minus just floating around somewhere in solution now that it has those the bonding electrons that it took from carbon. And it's just off somewhere in solution. Never to be heard from again, because remember all those partially positive hydrogens on the water molecule? They are going to surround and stabilize that negative chloride, and therefore chlorine is happy. It doesn't mind what's going on. It's gone. But I'm left with a carbocation. The reason I turned this into a tertiary starting molecule is we're looking at a mechanism that has an intermediate. And if we look at the intermediate, the faster the intermediate will, the more stable the intermediate, the happier it is to form, the more likely it is to form, therefore, the faster the reaction. And so once that carbocation forms, a water molecule that's floating around in solution happens to notice that there's a carbocation. The partially negative oxygen electrons say, hey, carbocation, let me attach. And that gives me my next intermediate, which is my carbon chain, the new bond that formed between carbon and oxygen. And now I have the oxygen with its 2 hydrogen atoms, only 1 lone pair, and a positive charge. Now here's the problem. Oxygen was greedy. Oxygen was like me and apple pie and ice cream this weekend. I should have stopped at 1 serving. I didn't. I bit off more than I could chew. I have no regrets. It was so good. But now oxygen has an extra hydrogen. It has a positive charge. It's an electronegative atom with a positive charge, and that makes it very unhappy. And so oxygen starts pulling on the electrons between itself and hydrogen because it's trying to compensate for the positive charge by getting electrons around it, which in turn makes the hydrogens very partially positive. And if the hydrogens are very partially positive, something else in solution is going to be attracted, happens to be another oxygen molecule. And so oxygen will reach out with these electrons that I'm showing you in purple, grab that hydrogen, breaking the bond between oxygen and hydrogen, collapsing the electrons back to oxygen. All right, let's do some quick accounting. As a reminder, and I've shared this before, I have ADHD. Can you imagine this was our session? I would lose my mind. And so that is why I do everything in color. It helps me focus and hopefully helps you also follow along. And I try to keep the electron colors the same throughout so that you can follow their movement. I don't want you memorizing this mechanism. Oh my goodness, I think my second is cold. I'm starting to feel it. I don't want you memorizing the mechanism. I want you to pay attention to what happens and why. So why did this oxygen attack? Because it's partially negative. Why did this hydrogen get attacked? Because it's partially positive. Why did oxygen get the electrons back? Because it was already pulling on it. Hydrogen can only have 1 bond. And so it has to collapse and break away. Make sure that every step of the way, the why behind what is happening is crystal clear. Otherwise, I'm going to say it again and again. This is the most difficult topic in Orgo 1 if you don't understand it. Yes, I'm so glad it helps and resonates. If you don't understand it, you will be overwhelmed. But after tonight, you are not going to be overwhelmed. So what do we have? We have oxygen that now has just the 1 hydrogen attached. It had the blue lone pair of electrons, which I'm going to move to up here. It also now has this purple pair of electrons from the hydrogen bond that broke away. So this is happy. It's neutral. This is my final product. What else do I have in solution? I have oxygen with 2 hydrogens, 1 lone pair, and then this set of purple electrons is a bond to the blue hydrogen that was grabbed from here. And that gives this one a positive charge. I said that this was an acid catalyzed reaction. I showed you how sulfuric acid was my source of protons in solution. What happens in solution, which I forgot to show you, is that as soon as sulfuric acid dissolves and the protons come off, water molecules will start grabbing it. This is called the leveling effect. You don't actually have to know that, so maybe forget I said that word. But what happens is you put a strong acid into water, it completely dissociates. And then what this gives you is just a source of hydronium in solution, like this. This is how the acid will actually end up. And so when I show my final product, the definition of a catalyst is that it gets regenerated, it doesn't get used up. This is my catalyst coming back. If your professor likes to see a balanced final product, just show the Cl- next to it. So it's a hydronium chloride in solution. And then this is the final product for SN1. If you followed along, if you're with me, give me some fire emojis in the comments to show that you're with me. And we're going to start talking about rules and side things and all the scary things that will make this so much more understandable. Question, what about the methyl group? What about the methyl group is called, I completely forgot about the methyl group. Thank you for catching that. Okay, I forgot that at any point, if something doesn't make sense, either you didn't understand, therefore I want you to ask so I can explain, or I made a mistake. And if you ask and bring it to my attention, I can correct it. And therefore, anyone watching this in the future will hopefully only be confused for the few minutes it took me to read your comment. Pop that on the screen. Thank you so much. Congratulations, a registered chemist. Guys, let's get a warm round of applause. I want to see applause in the comments. That is so awesome. Thank you for taking the time to stop in and share that. No matter what it is that you're working for, because I know students here are going for everything from laboratory work to the health field, medical, dental, pharmacy, veterinary, whatever it is that you're going for. This is a hard class, and if you work hard, you will get there. Congratulations. And I see a lot of applause showing up in the comments. Thank you, guys. This is awesome. All right, so let's now continue with all the little things that come up. When we did this mechanism, you notice I didn't just say this happens and this happens and this happens. It's a story. It's a drama. Trust me, if you can turn this into soap opera level drama, you will have so much of an easier time remembering this. A question. Yes, the live streams are automatically posted. And if you put live notes in the comments, I will reply with a link so you can get a PDF of everything I'm writing. And then you don't have to worry about taking notes. Yes, even if you're watching the recording. Can you go through shifts? Yes, absolutely. So I want to talk about all the little things that came up here. And so with this drama, we talked about how chlorine will pull and pull and pull and eventually break off. This right here is a very, very slow step. When you have a reaction that has a slow step, everything else is instantaneous. Water bumps in, instantly attacks. The hydrogen is partially positive. Another water bumps in, instantly attacks. And so if this, let's use exaggerated examples, if this takes hours and this takes seconds, then the rate of the reaction is only determined by the slow step and nothing else. That is called the rate determining step of the reaction. And so if we write out the rate law for an SN1 reaction, that is equal to some constant K that is different for each molecule. We don't care about that. Times, meaning we don't care about that unless you're running the calculations for this, which in organic chemistry you shouldn't, times the concentration of this starting molecule, the alkyl halide. Your professor may call it different things. It's just the molecule that has the leaving group. And when the leaving group hops off, that is the rate determining step. Notice there is only one molecule in the rate determining step. That makes this a unimolecular reaction. That is where that one comes from. A lot of times students will see that one and think one step reaction. No, no, no. This one right here was one step, two step, three steps, but one molecule reacted at a time. And that is why it is an SN1. Question. I know that for SN2, they do not work with tertiary. Why is this different with SN1? Jessica, that is an absolutely amazing question. I want to go back to carbocation stability. And also, I challenge you not to memorize that rule. I want you to understand it. The slow step of this reaction was all about the carbocation forming. And that means if I can form a carbocation, then I can have an intermediate, the water can attack, the deprotonation can happen, the reaction can happen. And so we have to look at carbocation stability to understand how fast this reaction will go. And professors will give you ranking questions for this. So one of the homework assignments for this live stream was to review carbocation stability. If you sign up for the notes, you will also get a link to, you'll also get homework in the email so that you can go back if you haven't done the homework yet. With carbocation stability, a quick summary here is if I have, we'll make that tertiary, we'll make that secondary, we'll make that primary, we'll make that methyl. Let me just show you what I mean. Tertiary carbocation, secondary, primary, and methyl. Tertiary is the most stable. Actually, let's do that right there. This right here is the most stable, and that is because carbocations are stabilized by the surrounding groups. So this is tertiary. It has 3 surrounding groups, and in the homework article, I actually talk about moral support and explain it in a little more detail. This is secondary, so it has fewer supporting groups. It's slightly less stable. I put 2 of these to show that the difference from here to here is a little bit, but this is night and day. This is a primary carbocation, and this is a methyl. A methyl is least stable. And for the sake of our discussion today, you will not see a methyl carbocation or a primary carbocation. They are so unstable that they will absolutely not form. Now, just a completely side note, as I'm going through this, I'm using very simple examples today because I want to make sure that when you're learning a new concept, the material isn't overwhelming. But once you get this, you have to do more advanced practice. You have to do tons and tons of practice to get this topic. And so if you're interested, I have a substitution elimination. So not quite after today, but once you study SN1, SN2, E1, E2, I have a complete midterm worksheet, not available on my website, but it is free. Just comment midterm and I'll send you a link. Yes, even if you're watching the recording so that you can save it for practice once you get all the material and you want to do the more advanced information. So if we're looking at carbocation stability, if my leaving group is sitting right there on a tertiary carbon, it's going to break away fast. Therefore, this is a faster reaction. If my leaving group is sitting right here, LG, leaving group meaning the thing that broke away, like the chlorine that I showed you in the mechanism here, it's more likely to break away from tertiary than secondary, but it is not going to break away from a primary and from a methyl. So we'll focus on this angle for the SN1, and then I don't remember who asked the question, I think it was Jessica. For SN2, I'll show you why the situation is completely reversed. A couple of comments have come in, so let me see. If SN1 rate law does not depend on the nucleophile, then how come a strong nucleophile cannot do SN1? Oh, that is such a good question. I'm going to turn that question around on you, and I want to ask you, what does a strong nucleophile have to do with this reaction? Because SN1 is a weak nucleophile, but once we get to SN2 and we talk about the nucleophile, I want you to pay attention to the difference in how it behaves, and that will answer your question. That will hopefully clarify your question much better. So Noelle, I saw your comment, and that's why I mentioned the midterm worksheet. And Noelle, as a study hall member, you already have access to everything with that. So email me if you want the direct links. And I'm seeing a lot of comments come in. Question on E1 and E2. It is on the midterm worksheet as well. If you're talking about a live stream, that is my plan for next week. So students voted on substitution elimination for this week. It was like over 50%, I think. And so I'm breaking it up. This way I don't have to rush. Because in the past, I've taught it in 1 hour. I've tried to teach it in 1 hour. Did not succeed. So we're going to break it up. All right, so let's continue. We have our carbocation stability that helps us figure out if a reaction will be faster or slower. And the way professors will put questions like this is something like, if you have this molecule and if you have, let's put 3 versions of it, they'll say rank the following molecules from fast to slow for an SN1 reaction, something like this. And what you want to do in this case is look at the leaving group. And I just gave you 2 of the same thing, so let me do that. There we go. We'll put a methyl group. You know, we'll put a methyl group there. This one right here is secondary. The carbon holding the leaving group is secondary. This one right here is tertiary, and this one right here is primary. Tertiary will be the fastest because it will form the most stable carbocation, therefore it will go quickly. This one is going to be the slowest to the point where it'll be no reaction for SN1. And that is because we cannot form a primary carbocation, which is what we would have here. And this one right here would be the middle, meaning it'll be not the fastest and not the slowest. Jessica, I answered half your questions so far. Let me know if that makes sense. And one more note I have is the carbocation formation is the slow step. I just want to make sure to reiterate, this is called the rate determining step, because this is where the rate of the reaction comes from. Right, so the next thing I want to talk about with an SN1 reaction is if I happen to have stereochemistry. For my starting molecule, I showed you this. I reacted it with H2SO4, and I simply gave you an H2O, and I simply gave you a product that has an OH. But if you look at this molecule, the carbon holding the alcohol for the final product is a chiral carbon. This is a chiral carbon. That means we have to account for the stereochemistry of what is going on here. And so for the stereochemistry, yes, the product is going to be chiral, but what do you think? Is it going to be R or S? Does it matter if the molecule started R or S? So for shits and giggles, let's, excuse my language there. Let's call this R because why not? And the answer here is that it is going to be still chiral. If we start chiral, we end chiral, but this will be a racemic mixture. A racemic mixture, I think of this as a race mixture, a mix of option 1 and option 2. We're not doing the chirality piece itself right now, but if you have trouble with chirality, email me and I'll send you some resources. A racemic mixture means that I'm going to have 50% R and 50% S within reason. Sometimes there are some extenuating circumstances which we're not going to worry about, because for the most part, just know that racemic means that we have a mix. And the reason for that is, let's say, let me just calculate this real quick. That would be 1, 2, 3, 4 is already in the back. Yeah, this is R if I put it on a wedge. So if I start with this molecule having chlorine on a wedge, when chlorine breaks away and I get my carbocation intermediate, what happened to the stereochemistry? Right now, this is an sp3 hybridized carbon atom. I did not show it because in line structure, hydrogen is invisible, but it goes to the back. When chlorine breaks away, hydrogen comes to the plane of the page. And what we have is sitting above and below, that's my MTP orbital. This right here is my carbocation. This is where the positive charge lives, in an MTP orbital. That makes this molecule sp, that doesn't look like an S. That makes this carbon here sp2 hybridized, which if you think about is trigonal planar, or as I tell you to refer to it, simply flat. If this molecule is flat, like a piece of paper, I have the option of attacking it from the bottom. That's not the bottom. Attacking it from the top or attacking it from the bottom. That means if a water molecule happens to bump in from the top, we get one stereo. If it bumps in from the bottom, we get the other stereo. And stereo meaning I get the R or the S, stereoisomer. And that means I'm going to get 50% top, 50% bottom. I get R and S in an equal mixture. So if the product is chiral for SN1, it will be racemic. If it is achiral, then that question is a moot point. So in this case, notice that it's chiral, but in the next example that we did, notice that this is not chiral, even though it's sp3 hybridized, even though it is three-dimensional. And that is because I have two identical substituents. These are both methyl groups. For a carbon to be chiral, I have to have 4 unique substituents. I have, well, the yellow is not shown. No, let's try a different color. I have ethyl, chlorine, methyl, and another methyl. That's 3, not 4. That's achiral. Therefore, my final product with the alcohol, methyl and methyl, is also achiral. And that's why I threw that in. So we have the 2 different options. If you're with me so far, thumbs up in the comments. If you have any questions, type them in. Let's see what else we have. Let me show you one more fun trick. So here's the thing. I showed you the step-by-step mechanism. And if your professor asks for the mechanism, then yes, you're going to have to show it. But if your professor does not ask for the mechanism, you do not have time to draw it. Let me repeat. You do not have time for the mechanism if it is not asked for. And so many students get into a pattern where the only way they can solve it is with a mechanism. So let's do this problem again, and then we're going to change it up. I want to show you something. If I have this right here, and I have my H2SO4 in H2O, and I have my final product that I have to draw, here is how you come up with a product. Identify your starting molecule. Get rid of your leaving group. We know it's going to go away. We know it's going to leave. Redraw the carbon skeleton without the leaving group. And then identify what your nucleophile is and add it in there. So what is my nucleophile? I know that H2SO4 is simply an acid catalyst, a source of protons in solution. So that's not my nucleophile. That means I have a solvolysis reaction. And what we're going to do here is the backpack trick. The backpack trick in summary, which I didn't think to put it in your homework, so I'll explain it. I want you to imagine that you, who are you, goes walking down the street. Who you are is who you are. And if you happen to put on a massive backpack, I know that's not the case now, but when I was an undergrad, we didn't carry tablets or iPads or anything like that. We had books, like actual, I even have some of them right here. Like, check this out. This massive textbook that weighs a ton. And depending on which classes you had for the day, you had 2, 3, 4 textbooks in your backpack. And that thing was heavy. Now, the you who is you, who's walking down the street, happens to be wearing a backpack. You are still you. You haven't changed. The only thing that changed is now you're carrying a little bit more weight. And so that is how I want you to think of when we're looking at molecules that attack. And I'll show you a couple of different examples. If I have my water, water is H2O. Think about the mechanism that happened. This molecule used a lone pair of electrons to do the attack. Then one of these got deprotonated. And so the atom that did the attack, that is the nucleophilic atom. That is all we care about. Attach your nucleophilic atom right there. Then one of the hydrogens had to get deprotonated. So let's go back to the mechanism. And notice that we had to remove a hydrogen because oxygen will have had too many bonds. So when we remove a hydrogen, we deprotonate it, we get rid of it. What else do I put onto this molecule? The backpack. It doesn't matter what the backpack is. It's everything else that is left on the molecule. I know this is a very easy example, and it sounds like such a crazy backpack thing. Like, why am I even talking about this? But let's apply this to a more complicated problem. First, though, before I continue, one thumbs up if you get the backpack trick, or if you get what I explained here. And the second thumbs up if you are good with the shortcut for an SN1 reaction. So let me review the shortcut. Identify your carbon chain, redraw it without your leaving group because we crossed it out. Find your nucleophilic atom, deprotonate one of the hydrogens, add the backpack. This is key. I want to make sure you're with me before I show you the next one. Typing the word thumbs up is perfectly acceptable. I will take that as well. You could just type 2x for 2 thumbs up if you don't want to write the word twice. I'm seeing a couple of singles and a couple of doubles. If you don't understand one of the pieces, let me know, but I want to show you something else. Let's make this molecule a little bit more complicated because your professor is not going to stop at the easy. So we are going to make this chiral with a bromine. We're going to react this once again with H2SO4, but this time I'm going to put it into a solution of methanol. Everything just changed. I challenge you that you know how to do this without a mechanism. Watch me do exactly what I did before. I recognize that I have H2SO4. That's simply a source of acid catalyst. It's simply an acid catalyst, meaning a source of protons in solution. I recognize that I have methanol as my solvent. That's my liquid. And that is going to be the attacker as well. Keep that aside. Look at the starting molecule. Bromine is a halogen. Halogen is a good leaving group. I cross it out. Redraw the carbon chain exactly as you see it without the halogen there, without the leaving group. We know that it's going to go over here. We know that this was chiral, so we know the product will be chiral, and I'll just write the word racemic. Some professors want you to write both products, and some professors will just accept racemic. Now, backpack trick. Watch. If I take my methanol, let's draw it out right here. I had my molecule of water that I showed you before. Now I'll take my molecule of methanol, which is a CH3OH. And another common one you're going to see is ethanol, which is a CH3CH2OH. Notice how they all kind of look the same. Here we have our attacking nucleophile. They all have a proton that gets deprotonated, and this right here is simply the backpack. And so for this reaction, I add my oxygen, and then I add my backpack. CH3, that is it. No mechanism required. Now, let me know if the backpack trick makes sense. Mariam, wait, how can I don't know what you're trying to ask. If you can just let me know which part you didn't understand, and I'll happily explain that again. Question: how do you know when sulfuric acid is being used as catalyst versus being utilized as a reactant? That is a very, very good question. Sulfuric acid is a catalyst. And so if you drop that into a polar protic solvent, if you drop it into a liquid that has protons like water, methanol, ethanol, any type of solution that is good at stabilizing charge, sulfuric acid will immediately dissociate 100%. It's one of the strong acids that completely dissociate, and you're going to get a source of protons in solution. There are a couple, I don't know if you have to memorize them in organic chemistry, but there's a couple of really strong ones like HCl and HClO, ClO4, 3. I don't remember if both of them are very strong. I should know it. MCAT students, you absolutely have to know it. I just haven't looked at those in a while. But strong acids, complete dissociation. All right, so that is the shortcut for an SN1 reaction. That kind of covers everything. So let's go ahead and move on to SN2. SN2 is also a substitution reaction, also nucleophilic. So it's going to use a nucleophile. And the 2 tells us that it is a bimolecular reaction. Bimolecular, so substitution means that we swap. Nucleophile is what attacks. Bimolecular means 2 molecules at a time, not 2 steps. This is 2 at a time. And so that means this right here is a 1-step reaction. A single step. And so, do you think carbocation stability is going to play a role in the SN2 reaction? That was a trick question that for some reason professors don't think to clarify. A carbocation intermediate is an intermediate. If this is a one-step reaction, there are no intermediates. And so I never, ever, ever want to see a carbocation in an SN2 reaction. This alone can save you so many points. There are no intermediates in an SN2 reaction. So let's take a look at, before we look at the mechanism, I want to talk about the nucleophile. I forget who asked before. I apologize, but I do want to make sure I answered your question. If I have a nucleophile that attacks, I can have a strong nucleophile or a weak nucleophile. If the nucleophile is attacking, I want you to think of it as, I think the example I used in my videos, we'll go with that example, is a kid on a swing. So I want you to imagine that there are children at a playground. And I haven't used this example in a while. My son does not like swings, like at all whatsoever. Ever since he was a baby and we tried to put him on a swing, nope, he would scream and cry. And now that he's a little older, he's 3.5. He watches the other kids on the swing, and I could see in his eyes, he wants to, because that's what they're doing. But the moment he gets on the swing, no like it, and he comes off. So I want you to imagine that there is a kid sitting on the swing, and they're having a grand time, and they're liking it. And then there's another kid who wants to, so make this kid orange, no, green with envy, right? And there's another kid who wants the swing. Now, there are two options for this kid to get the swing. Option one is they can wait and wait and wait. This is going to be very slow because this kid has no idea if this one wants to stay on for a minute or an hour. And if the only way they can get the swing is to wait, it will be a very, very, very slow process. Option two is you just push the kid off. I don't know about you, but if I push someone off a swing, that swing becomes immediately available and now it's all mine and I don't have to wait. I'm not going to push any kids off the swing. But the idea here is that the wait is slow and the pushing the kid off is fast. This is the difference between an SN1 and SN2 reaction. Now, if you're thinking of what would happen, why would one happen over the other? The wait is when you have something that is weak. Size in this case doesn't matter. But if you have a weak or timid or shy kid, they are not going to push anyone off the swing. But if you have someone who is strong and not afraid to use it, a bully, that bully, say this kid is 10 years old, this one is 4, this 10-year-old is having a bad day and does not mind being a bully, this kid doesn't have a chance. This kid is gone from the swing in 2 seconds, pushed off, crying to their mother, and now this kid gets the swing. And so what we're looking at for an SN1 reaction is this is weak. This is not strong at all whatsoever. And this is the shy kid who is quiet, who is weak, who cannot push anyone off the swing. And they wait and they wait and they wait. What are they waiting for? The carbocation formation. When the chlorine leaves and a carbocation is formed, this is the swing having been vacated. And now it immediately gets grabbed up by the weak kid because it's available and they don't have to push anyone away. With an SN2 reaction, it's the exact opposite. If I have a molecule, let's draw it kind of sideways. We'll make this a methyl chloride. And it's purposely drawn this way so you can envision what's going on. Let's make it 3-dimensional. So this one is coming out of the page, going into the page, down in the plane of the page, and this is this way. If I have a very strong nucleophile, and the starting example I used was NaOH. If NaOH, my very strong nucleophile, shows up, that is really just an OH minus, like this. Oxygen with a negative charge, he wanted the negative charge. Oxygen likes negative, but it is strong, it is angry, it's carrying the burden, it is not happy. It finds a partially positive carbon because chlorine is partially negative, and it just attacks, bumping that chlorine off. It's not waiting for chlorine to leave, it bumps the chlorine off. And what you get now is the molecule that you had in the beginning, chloride, was kicked off together with its electrons. Take your electrons and go, I want the swing, negative off somewhere in solution. And now attached on the other side, you have the OH. So a couple of things that just happened. Let's talk about one step at a time to make sure that you're with me. I said strong. What makes OH minus a strong nucleophile? We already know that nucleophile is nucleus loving. That is something negative or partially negative. What makes it strong is what makes anything reactive in organic chemistry. If you haven't caught this in the million other times I've mentioned it, happy, stable, unreactive. If you are happy, you're kind of calm, you're chill, nothing bothers you, you're not getting up for anything, you're not going anyway. But if you are in a bad mood and you're just having a bad day, you're unhappy, you are unstable, you're a lot more likely to snap at someone or to say things you wouldn't if you were calm. And that makes you very reactive. So what gives a molecule a temper tantrum? What makes a molecule unhappy? Charge. Charge is a burden. And even though some molecules can carry the charge more than others, a charged molecule is unhappy. And if it's carrying a negative charge, it will react, it will attack. And so your strong nucleophiles are your negative nucleophiles. Your O minus. So for example, OH minus, CH3O minus, N3 minus, what else? SH minus. Notice the negative. These are all carrying a burden of charge. That makes them strong as opposed to their neutral counterparts, which would be H2O, CH3OH, HN3, H2S. I just had to think how to write that, right? These are your neutral, and your neutral is not carrying a burden. These would be weak, or we can just call them stable. But these right here are your negatives. The negatives are angry. They do not want to wait for the kid to get off the swing. They will attack the kid and push the kid off the swing if they can. Now I want you to imagine that this kid is on the swing, but behind the kid, there is a grown-up. Do you think that kid is going to push the kid off the swing? Let's assume they're not afraid of the grown-up. Let's assume instead that the grown-up is simply a physical presence that happens to be in the way. The way you push someone off the swing is you go behind them and you just kind of shove them right off. But if there's a grown-up standing behind the kid, you can't access the kid on the swing because there is a grown-up physically in the way. That is why we have to look at the starting molecule to see about being able to carry out a reaction. If there is steric hindrance in the form of substitution, substituents are going to hinder the reaction, and that means it's going to slow it down. The example that I gave you was a CH3Cl. Notice that this is a methyl group, a methyl alkyl halide holding a leaving group. This is going to be the fastest reaction because hydrogens are so small that no matter where the nucleophile comes from, anywhere around the molecule, it can access that carbon, attack it, and bump that chlorine off. Slightly slower is a primary leaving group. So if I put the chlorine on the primary carbon, this is still a relatively fast reaction because the nucleophile, which I like to write as Nu, can easily come and attack right there at the primary position, kick out the chlorine in one step, just push, and it comes right off. That's a pretty fast reaction. Same thing with the secondary in that it's slightly slower, and that is if I now put my chlorine at the secondary position. Now we still have to find a way to get the nucleophile in from the other side. It will come in with a backside attack. This is called a backside attack. I don't know if I mentioned that word before. Where did I draw it? Right here. This is called a backside attack. And when the nucleophile comes in, the chlorine gets kicked out. That is still possible. However, if I increase the degree of substitution here, And this time I give you a tertiary leaving group with a chlorine right here. There are too many substituents. The nucleophile wants to attack, but it cannot get there. That is why there is no SN2 for a tertiary reaction. I don't remember who asked that question first, earlier. It's not about the strong nucleophile cannot do SN2. It's that the strong nucleophile wants to do a direct attack, but it can't reach. And if it can't reach, it cannot kick anything out. Therefore, the reaction cannot happen. And so SN2 is going to prefer a less substituted LG, stands for leaving group. All right, let me just, I kind of been talking in circles right here, so let me just make sure. We looked at the mechanism. We looked at the rate of the reaction. And speaking of the rate of the reaction, notice that there is only one reaction arrow. This right here was a single step. This is a one-step reaction. Therefore, bimolecular, two things reacting at the same time, attack, kick out simultaneously. And that is why this is a reaction with no intermediates. However, what we do have to consider is now, if two things are in the only step, the rate determining step, then the rate law for this reaction has to account for them both. So the rate of an SN2 reaction is equal to some constant K that we don't care about because it changes for each reaction, times the concentration of the molecule that has the leaving group, we'll call that the alkyl chain or the alkyl halide, times the concentration of the attacking nucleophile, and that gives us our rate for this reaction. Notice that I have two things here. 2 is how we get the bimolecular, and that is how we get the 2 in, I don't know why I did that in red. That is how we get the 2 in an SN2 reaction, a single step, 2 molecules at the same time. If you're with me so far for SN2, thumbs up in the comments to let me know. Questions, of course, keep them coming. It can only attack from the back, yes. So let's take a look at stereochemistry. For the starting molecule, the first reaction I gave you on the screen, I showed you that we had a chlorine right here. This chlorine is up and out of the page. That means if a nucleophile, and I had given you NaOH, so if the nucleophile OH minus tries to attack from the top, it can't get there. It's blocked. There's a chlorine in the way. So the OH minus is floating around in solution until eventually it realizes, oh yeah, I can attack from the bottom. Not that I'm only allowed from the bottom, it's there's no other access. This is the only way to attack. The bottom under the page dashes, and that means that for the product, you will have the incoming nucleophile, the alcohol, undashes. Question. In an SN2 reaction with spectator, does the spectator get debonded from anion? Okay, that is actually a very, very good question. So let me talk about the spectator in the same explanation as showing you the shortcut for an SN2. Shortcut in the comments if you want to see a shortcut. I didn't call the SN1 shortcut, but I hope you assumed and recognized what it was. If I am given a reaction where I have, let's do the same one so we can use what we already know. And then let's go with the question that just came in. So we have NaOH in DMSO. Actually, I forgot to talk about the solvent. Let's talk about the solvent and then come back to the shortcut because I do see a lot of the questions coming in. If I forget, remind me. Solvents. Solvents are very, very, very important. In our SN1 reaction, when we talked about the backpack trick, where did I talk about the backpack trick? Right here. Notice that all of the solvents here have the hydrogens. These are considered polar protic solvents. So let's break it down. So we have both of the solvents are, both sets of solvents will be polar, but we have the protic and we have the polar aprotic. What is a protic solvent? Polar is whatever. It's the same thing. The protic, aprotic is what we care about. And in answering this question, do you like to have fun? Just a side question for you. Yes or no, do you like to have fun? While you're typing that in, protic comes from the word proton. Proton is an H+. That is what we're looking for. If we have a solvent that has an H+ on it, specifically what kind of H+, I am seeing yeses and of course in that you like to have fun. Hydrogen also likes to have fun, specifically FON. You're not going to see fluorine in organic chemistry reactions like this. Pretty much not going to see it in like more than a couple of reactions. For solvents, we're going to look at oxygen and nitrogen. If you have a hydrogen on oxygen or nitrogen, then that hydrogen is capable of hydrogen bonding. So hydrogen bonding is when a hydrogen likes to have fun, F-O-N. And what is happening here is when the oxygen is attached to the hydrogen, for example, in a water molecule. We talked about this before, but I didn't call it protic. We said that the oxygen is going to hog the electrons, making it partially negative. The electrons are being pulled away from hydrogen, making it partially positive. That means if I bring another molecule of water, they're going to have a very, very, very strong attraction. How strong and powerful is this fleeting bond between oxygen and hydrogen? If you have ever belly flopped into a pool, you're trying to dive and you kind of go flat and your belly, you just hit that water so hard and it feels like you got punched by a concrete wall. That is how strong these hydrogen bonds are. That is a protic solvent. And so think of anything that has oxygen or nitrogen with a hydrogen on it. For example, you have a water molecule, you have any alcohol. I've shown you methanol, ethanol. You can have ammonia. So for example, nitrogen. You can have an amine, nitrogen with 1 or 2 R groups, not 3, because now we lose the hydrogen. But these molecules right here, these are polar protic solvents. Polar protic solvents can solvate and stabilize charges in solution. Stabilize charge. And that is why they do so well in an SN1 reaction, because SN1 is full of charges. We have our acid catalyst, that's an H+. We have the leaving group that comes off, that's a negative charge. And they all get the carbocation, right? That's important. Ariel, I like your honesty. So SN1 reactions will prefer a polar protic solvent. But in an SN2 reaction, that nucleophile is angry. If you take an angry nucleophile and you say, calm down, it's okay, we're going to surround you with happy charge, that nucleophile is going to chill out. And that nucleophile is not a strong nucleophile anymore. You want a solvent that does not chill out the nucleophile. You want an aprotic solvent. That means if you have hydrogen in the solvent, no fun hydrogens. No fun hydrogen. And depending on, let me know in the comments if you have to take the ACS exam, because ACS students, you have to memorize name, molecular formula, and structure for all of the common polar aprotic solvents. Let's see if I remember them. I haven't taught this in a while. We have DMF, DMSO, aceto, there's 5 of them. Let's see if I remember all 5. Acetonitrile, acetone, and ether. Okay, look at that. It helps if I would have notes for this session, right? I'm going to check my notes after to see if I missed anything. DMF is dimethylformamide. Form is a single. Methylamide is a nitrogen. CH3 with a hydrogen. DMSO is dimethyl sulfoxide. So I'll draw the sulfoxide with a dimethyl. Acetonitrile, aceto tells you 2 carbons with a nitrile. So that's a C-triple-N right there. Acetone is just a 3-carbon ketone. And ether could be anything that is ROR, but THF is a very common one that shows up. Tetrahydrofuran is just a cyclic ether. Julie has to take it. I do, but not for legitimacy. I don't understand what that means. But Nicole, in your case, you should know them for the MCAT as well. I know you're taking that soon. So definitely. How many MCAT students here? Just let me know in the comments. I forgot to ask in the beginning what brings you here today. I usually do, but completely forgot. Also, I just realized we are at the hour. Keep going or wrap it up. What do you think? I'm good to keep going for a little bit, and I think we're almost done. Now, can you imagine we tried to do elimination as well today? That would be very, very fast. Okay, so what do we have here? Notice that every single hydrogen that I drew here and the hydrogens that are implied in the line structure would be here in the ether, like that. They are sitting on carbon. They are not sitting on oxygen or nitrogen. They have no fun. And so if I bring an OH minus into any of these solutions, there's nothing to calm it down. If I take an OH minus and I throw it into a solution of water, in a solution that likes to have fun, that water molecule or the water molecules will immediately surround it like this. Partially positive hydrogens around the negative oxygen. And this right here is calm. It is not an angry nucleophile anymore. Therefore, it won't work for SN2. If we want that nucleophile to stay angry for SN2, we need a polar aprotic solvent. All right, so now if you're good on the solvents, thumbs up in the comments to let me know. If you have questions, type them in. Let's go back to the shortcut. First, I want to analyze what I have here. I have a secondary leaving group. I have NaOH and DMSO. How do I recognize that it is a strong attacker? A strong attacker is negative, but this doesn't appear to be negative. This appears to be neutral. That's where you want to recognize. Anytime you have Na plus in front of a molecule, that is simply a counter ion. It is a spectator going all the way back to who had asked that question right here. So the spectator ion is just there for a balanced equation, but just like the H2SO4, that was a source of protons in solution. What I forgot to talk about with the H2SO4 is that when you get a source of protons in solution, you also get the HSO4 minus or even the SO4 2 minus. This does nothing. It's a spectator. It disappears, never to be heard from again. And so if you recognize that, where are we with the mechanism, with the reaction, with a shortcut here. Okay. If you recognize the spectator, it's just there to balance charge. It breaks away. It goes somewhere. It's probably not very happy because it doesn't have anything to latch onto like it does in a protic solvent, but it just disappears, never to be heard from again. And what we care about is that we have the OH minus, which brings up the shortcut. Redraw your carbon skeleton as you see it without the leaving group. If you have stereochemistry, which we do, draw it with the opposite. So I have a wedge. I'm going to draw the opposite. That will be a dash. I will grab my nucleophile and attach it. And that is my mechanism-free SN2 product. Let's try it with something scarier. These notes are completely out of order, but you should hopefully still be able to follow along. Let's try, well, professors like to show rings. Let me know in the comments, when you see a ring, does that automatically just scare you, make you feel like, oh my goodness, this is so much harder? Because professors love to do that. What I want you to recognize is the shortcut is based on logic, and the logic applies no matter what. So let's go with NaN3 in DMF. All right, so what do we have here? We have a secondary leaving group. We have an Na plus positive spectator. That means this is negative. That's my nucleophile. DMF is a polar aprotic solvent. That means it likes the SN2 reaction, and only the SN2 reaction, does not like elimination. Hint for part 2. And so what we're going to do here is get rid of the leaving group, redraw the carbon skeleton exactly as you see it without the leaving group. See, it doesn't matter that it's a ring because the logic is the same. Redraw it exactly as you see it. Put the stereochemistry exactly opposite. Find the nucleophile that did the attack. Add it. And that right there is a product, is the correct product without having to work too hard, and definitely no mechanism. Let me see. I have to take it as my final. It will be submitted to the ACS, but grade will only reflect the questions we were taught. Okay, that makes sense. A lot of times in Orgo 1, the ACS, because it covers Orgo 1 and 2, I don't know if they have a just Orgo 1, but professors will just, they will regrade it. Like if you get a 23 out of 70, they'll say, no, it's really just a 23 out of 35 or something like that. Jessica, well, I'm so glad that you joined for the first time. Hopefully I will see you more. And also I have something very special. I don't know if you're still around. Make sure to watch the recording or check the email that I'll send after, because I have something special to share at the end. So hold on. I have something very exciting. Noelle, I know, unfortunately you don't, but the good news is that you have the help that you need. You are here and you're doing well. So that is what we care about. Yes, it scares me. Well, that was before, right? Does it still scare you when you apply this shortcut? Question, remind me, does the trick work for both SN1 and SN2? For SN2, it's this one. For SN1, I showed it to you with a slightly different approach right here. Is this where I showed you the trick? If it isn't, I'm just going to put the word shortcut on here anyway. And remind you, identify it's an SN1, redraw the carbon skeleton exactly as you see it after crossing out the leaving group, find the attacking nucleophile, which I didn't show you the trick for this, so I'm glad I actually went back, because you don't want to draw this out on your exam. Just notice that oxygen, that's your nucleophile, that's the hydrogen to deprotonate, that's the backpack. There's your shortcut, there's your product. This is chiral, so it is racemic because it's SN1. This one is chiral, but it is not racemic because we have an inversion of chirality, an inversion of configuration. The stereochemistry flipped because it's a backside attack. Cielo, the recording is immediately goes to YouTube, so you will have access to it. And of course, don't forget, if you put live notes in the comments, you'll get the PDF from today. Put midterm in the comment for my midterm practice worksheet on substitution elimination reactions. It is not on my website, but you can have it anyway. All right. Given the time, and given that I mentioned the midterm worksheet, and given that I have something exciting to share, let's say we wrap it up here, knowing that you will still want to do a lot of practice, because obviously this is going to take some practice to sink in. But what if you could access an entire boot camp on everything substitution, everything elimination, and then just intense practice sessions, practice problems where I go through this trick and that trick and that trick? That is a mini boot camp I have taught a couple of years ago on substitution elimination reactions. And I also have the midterm practice worksheet that you're signing up for. That is just the worksheet and the answers. But what if you could watch me break down every question step by step? This is what I'm doing. This is how I'm doing it. This is why I'm doing it. Knowing that substitution and elimination is the most difficult topic in organic chemistry 1. And if you haven't gotten to it yet, you're probably starting to get an idea of why it's so hard. Do you think that having access to that mini boot camp and to the solutions for the midterm would help you better understand this topic? Because if yes, and let me show you, where do I have it? Right here. So this is, I called it workshop, but this is the boot camp. So session 1, we go through substitution and elimination. Session 2, session 3, we go crazy. Session 4, we go even crazier. The PDF notes are, is it showing on the screen? No, it is not showing. So you get full PDF notes. Oh, I can actually click share this tab. There we go. full PDF notes with everything. So notice just how much we went through. And as you can see, there is Newman projection problems, benzene problems, ring problems, chair problems, just everything that your professor could think to show you, broken down step by step. And then I have the substitution elimination practice quiz on my website, video solutions, and the substitution elimination midterm practice worksheet solving session. This thing was edited down to 2 hours and 12 minutes, along with the PDF step-by-step answers. If this is something that you would be interested in, you have 2 options to get it. I will tell you option 1, but I vote for option 2. Option 1, this is available on my website. I charge $150 at $149. I'm rounding up. And you can buy this at any time. That will give you access for 60 days. Option 2 is where I am going to make a very, very big ask of you. And I think you might like it. So in less than 2 weeks, and I'm totally not freaking out. And what I mean by that is I'm totally freaking out. I will be running my first ever marathon. This is the New York City Marathon on November 2nd. And I'm running this with an organization called Share It. So I am on Team Share It, where the organization, what they do is they help women and their families who are going through treatment for breast cancer and ovarian cancer. The reason I'm doing this is back in 2010, I lost my grandmother to breast cancer. And she was just, I explained it on the fundraiser page, but she was someone who was really, really special to me. And I'm doing this in her honor. I mean, I loved her so much. She is my son's namesake. He was named for her. And so I'm doing this in her memory, in her honor. And my goal is to raise $5,000. If you've been with me for a while, you've already seen this before. But what I am asking or begging is if you would consider making a donation. As I said, the bootcamp itself is $150. I'm asking for a donation of just $25 or more. I know that for a lot of students, because of just everything you have going on right now, the cost of classes and books and just everything else, making a big ask isn't necessarily feasible, doesn't necessarily work for you. And I want this to be the kind of thing that would work for you and still make it accessible. And so if you can donate $25 or more to my fundraiser, less than 2 weeks to go, still about $2,000 to go. So I'm really, really hoping we get there. Then you can have everything that I just showed you. The substitution elimination bootcamp, that is the 4 videos, just going from beginner to advanced with tons of practice. The substitution elimination quiz with the video solutions. The quiz is available on my website, but you get the video solutions. And the substitution midterm practice worksheet solving session as well. All of that for a donation. The link is, I should probably do a banner. Hang on. Here, I'm going to put the link on the screen. It's layerforsi.com/marathon. That should redirect to, here we go. That should redirect to the fundraiser page. Let me just check it, make sure that it's the right page. And that is where you can make your donation. This is an organization that does such amazing work, because when a family is going through something like this, the person going through this and their family members, their entire lives are completely uprooted. I have a friend who just got diagnosed with pancreatic cancer. His entire everything just paused because his life right now is all about chemo and treatments and appointments for this and appointments for that. And this is a lot. And so they provide so many amazing services for the patient, but also for the family. And to be able to raise $5,000, this goes a very, very long way with what they can do. And this not only means a lot to me because of just the fact that you're supporting me, but also because of how much my grandmother meant to me, that you will be helping me honor her memory. And I would really, really appreciate it. The link up is on the screen. And what happens is after you donate, just forward me the receipt. Just hit reply to any email that I've ever sent you. It's the same email address. forward me the receipt, and then my assistant or me, whoever sees it first, is going to send you a link with all of the things that I promised, and you will have access through the end of the semester. So we'll just call it the end of December. This way I don't have to worry about when your semester ends. I'll make sure that you have access through finals. Hilda says, I'm getting an error on the worksheet link. Is anyone else getting an error on the worksheet link? Can you place that in the chat? Yes, layerforsight.com/marathon. That is for the fundraiser. Let me just make sure that link worked. Yes, same here. Okay. You know what? I think I know what happened. Give me a moment. Let me get you a better link. Okay. If you were having trouble, I know what happened, and I SOS'd my assistant. There we go. I had SOS'd her about something else, and I didn't realize that she changed the link. So I just put the right one in the comments. Thank you, Cielo. I need like 6 more months to train for this thing, and I have about 10 days. Yes, a $25 donation or more, but I'm asking for at least 25, and you will get everything that I mentioned with my deepest, sincerest thank you, because this is gonna be something. Okay. All right. If you have any questions on anything that we discussed today, go ahead and type it in the chat. Once I log off, YouTube will keep me connected for a couple of minutes. And so I will stick around and answer questions. What is going on? I'm not sure if you mean like you just logged in, what is going on, or what is going on with the link. Thank you so much. You are very, very welcome. I'll hang out in the chat, post all your questions. If something doesn't work, if something is broken, just email me. I'll hang around. The notes will go out probably in the next 30-ish minutes, and then we'll go from there. I just joined. What is the marathon? What is the donation? Okay, so email me. I think it'll be easier for me to just explain all of that. And you'll probably want to rewatch the whole live stream. So for Nord's Midnight, here's what I want you to do. If you need help with substitution elimination, if you sign up for the notes, hold on, I just lost the other link. If you sign up for the notes, the link that I just put in the chat, you're going to get the notes, the recording, and all of the details. Thank you so much. Yes, next week will be E1 and E2. It'll be part 2, continuing from what we started today. All right, good night, everyone. I will see you soon. And cross your fingers for me that I'm not sick, because my nose is definitely, what did my son tell me today? At dinner. So his nose is leaking, right? He's 3. He doesn't think about a tissue. So I grab him a tissue. I wipe his nose, and he says, Mommy, I think my nose is broken. Why is your nose broken? He says, because it's wanting boogies all day. So I think my nose is also broken. On that note, have a wonderful evening.